All right, boys and girls, I just want to real quick review pH with you. You've learned what an acid is, or at least some properties of an acid. You know it's related to pH, and you probably know what I'm about to say. Hopefully, this is a review, or it could be your first introduction, and then you go back and do the lesson and learn better what it is. So, first, why is it important? I didn't type this question up here. And if you want to write this stuff down, go ahead, but I would wait just because I'm going to fill in this middle stuff here. So why is a pH scale important? It's important because it's a measurement of hydrogen ions. And hydrogen ions, as you know by now, are represented as an H to say it's a hydrogen atom, but it's an H plus because it's a hydrogen atom without its electron, meaning it's a lone, as in a lone proton, or a naked, is another way we refer to it, naked proton. Okay, it's a lone or naked proton. Okay, that's all a hydrogen ion is, just as a review. Okay, so in your stomach, this is probably the most familiar place, your stomach or a car is where you've heard of acid, of course, and you know that acids are there. So hydrochloric acid's in your stomach, and it's called an acid because there's a high amount of hydrogen ions. Okay, that's what this H plus is, hydrogen ions. What that does in your stomach, of course, is any food you eat or anything that comes in your mouth and gets into your belly, goes through an amount of sterilization process. I mean, the protons are attracted to those molecules and the atoms that make up your food, and it just totally disrupt the bonds. As you know by now, chemical bonds are held together due to the valence electron number, and it's very special. But when a whole bunch of protons are in the environment, those protons are positive charges, and they will attract those electrons. And sometimes they attract enough of those electrons that the electrons will leave the orbit of whatever element they're a part of. And if you have this positive charge over here, that electron may come, and we're going to form a complete hydrogen atom, right? And that hydrogen atom will be picked up and bound to another molecule. So you have an element or a molecule right here, and if you have a whole bunch of hydrogen ions, then those positive charge protons, those lone naked protons, will pull away, very much like the free radicals we've talked about. Oh no, that was the other class. Electrons, and it'll totally break this bond. And that's kind of what we want in the stomach. We want to break down some of those large bonds so that you can use the molecules in your body. Because we don't need pepperoni, scrambled eggs, or cottage cheese on our body. We need the molecules that make it up. So we have to break them down. And so this happens in a very general way in your stomach because of hydrochloric acid. All the protons do that. So car batteries, another reason way to look at it, so on our stomach, it's acidic because it's high proton. We use that to digest food or begin to break down food for digestion. But in a car, the acid, of course, if you have a high, so this is sulfuric acid, and if you have a high sulfuric acid, it's, again, positive charges, well, then you can send a current through that of electrons that's going to attract. And in that case, batteries have the positive and negative separated electrons from protons, and they want to combine just like this, but we physically, and in a car, it's physically separated. But the moment you ignite that switch, then you're removing the barrier in the battery, and those protons and electrons flow towards each other, and that flow of electrons is called a current. Right? A current of electrons, that's a current of electricity, and it can be used to power something. Okay, so pH is different in various places. In your mouth, it's about a pH of 7, a little acidic. It's about really probably 6. In your small intestines, it's a pH of about 11, 10 to 11. It can be 7 and then 10 and 11. Just a matter of inches. And then in your stomach, you have a pH of about 3 or 4, except for when you're eating, it might drop to as low as pH of 2. So you've heard me say now pH of 2, 4, way up here, 11 on the scale, and so forth. So what is the pH scale? It's a scale of measurement that ranks the amount of hydrogen ions from 1 to 14. Well, I guess you could say 0 to 14. 14 is the highest number that you can attain on a pH scale. And so you now know that the H represents the hydrogen ion. So it's the power or the potential of hydrogen, however you'd like to say that. Probably potential I like better, but I'll just go ahead and, since I already wrote power of hydrogen, okay, to do work. There's so much of it, it's going to attract and distract, okay? So that's what the pH scale is. It's a scale of 0 to 14 where 7 and below is considered a high pH, that is high amount of protons. I'm going to erase a part of this here real quick. Power of hydrogen. And then above 7, that is up to 14, would be a low number hydrogen ions. Now, I don't mind getting, I probably will, just to explain, I won't hold you responsible for understanding why. The smaller the number means the more the hydrogen, and the larger the number means the less the hydrogen. It has to do with what those numbers represent. So again, 7 is neutral, right in between. 0, the low pHs are very acidic, and 7 to 14 would be low acidity, or what we call basic, okay? So I'm going to erase this, clear some space on it real quick, and I'm going to draw you what this is based on and try to explain that scale just a little bit more. So what is, oh no, what did I erase that? Well, you can rewind briefly and see what was right there. So what is it based on? It is based on, hold on. It is based on water, basically. So if you have H2O, now this is not going to be a balanced equation, but for simplicity, it's going to be the empirical formula I'll show you, and we can balance it if you'd like in a few moments. But first, water. 1 in about 500 million water molecules randomly dissociates, the dissociation reaction. And when it does, you're going to have to recall from the beginning of the semester that oxygen with an atomic number of 6 is very, or 8, I'm sorry, 8 is very powerful. Very electronegative. It tends to attract electrons. So if when it dissociates, one of the hydrogens leaves, the oxygen is bigger and stronger than that atomic number of 1 in a hydrogen, and it's going to keep the electron from that hydrogen. So it dissociates into an OH and an H. So you can see how that's balanced there. You have H2O randomly dissociates into the products of hydroxide ion and hydrogen ion. So why the negative and the positive? Because again, the oxygen held on to the electron, and so really all that dissociated, all that left was the lone naked proton. To draw a picture of what this looks like is you have water, and this is the oxygen, these are the hydrogen. And so this is a polar covalent bond. The oxygen tends to hog the electrons. So the 2 electrons from hydrogen tend to spend more time around the oxygen. And when they split apart, you have that oxygen and now 1 hydrogen, and then the other hydrogen over here. So a hydrogen is 1 proton, and if it lost the electron, it's going to have that positive charge. And that electron stayed over here, so now it's going to have the negative charge. So we have an OH, or what we call hydroxide, or hydrogen, hydronium, hydroxide, and then we have hydrogen ion. Hydrogen ion, right? So "-ide" and ion are the suffix we give it. So OH and H. What pH is measuring is this right here. So look at this definition. If you had pure water, no minerals or anything that's distilled, then anything that you added to water that resulted in more hydrogen ions, that would be called an acid. So acids donate those protons or release hydrogen ions, however you want to say that. And anything that you added to water that resulted in less protons would be called a base. So bases accept or they remove hydrogen ions from the environment. Okay, and you had some examples of that in the notes and in the reading. So what I'm saying here is in pure water, all right, I'm just going to erase a part of this here, the circles. So in pure water, what you have is for every one of these hydroxide ions, you're going to have one hydrogen ion. So these are always equal to each other and therefore neutral. What we call, and I won't hold you responsible for this, is the ionization constant of water. Whenever you add up in pure water all the hydrogen ions and all the hydroxide ions, you're always going to get, and this has been empirically tested and it's pretty phenomenal, you're always going to get this number of ions, okay? Which means that you have half of that. What's half of that? -7. And what's half of this? Or the other half, what am I saying? -7. So you have that many hydrogen ions and you have that many hydroxide ions. They equal each other, right? You add them up. So the thing about water is that just as frequently as it dissociates, it will also reassociate into water. Clearly, because as soon as it breaks apart, you say, hey, I'm negative, hey, I'm positive, all right, let's get together, and you're right back to water. And so this happens interchangeably, constantly, all right? And it was measured, and we called it the ionization constant of water. That's what the W stands for. And you never have more or less than this ion concentration. So now, when you have this number, and I'm going to go ahead and erase this over here. You should have that in your notes now. So whenever you have this number of hydrogen ions in pure water, you're 7, and that is neutral. Now anything, and you can see that throws this number off. If this number all of a sudden released more, first let me draw this number. That number looks like this. Whoops. 1, 2, 3, 4, 5, 6, 7. That's what that number actually looks like. Okay, let me erase the 1. All right, so you have, that's what 1 times 10 to the -7 is. You come back 7 times. 1, 2, 3, 4, 5, 6, 7. Don't have to remember the details of this for a test or anything. This is just for your understanding of the pH scale. So you have equal numbers. You also have 1 times 7 is 1, 2, actually 1, 2, 3, 4, 5, 6, 7. So they're equal. Now you tell me, what's a bigger number? This or this? Clearly, right? It's greater than. What's bigger? Right? This or this? Clearly, this is bigger, right? So if we continue doing that and playing this game, you're going to get the idea. So let's do it 2 more times. What's bigger? This or this? And you're right, this is bigger, okay? So the way we represent, let's say this number right here is 1 times 10, because that's what it is, times 10, 1, 2, 3 times. Okay, 3 times. Because you went to the left, it's going to be a negative. That's how many times 10 would have, the decimal would have to go to the left 3 times in order to be the actual number. So we represent this with a scientific notation. So think about that. 1, 2, 3, 4, 5, 6, 7 is 1 times 10 to the -7, because you have to go back 7 times to the left to get the actual number, okay? 1 times 10 is 7. So what would 1 times 10 to the -14 look like? Yep, you would have, you would have 14 zeros, or at least 13 zeros in front of that. So now, if we just use scientific notation, let me draw this for you, and you tell me which number is bigger, 1 times 10 to the -14 or 1 times 10 to the negative 1? Which one's bigger? Well, now that you know the decimal represents how many places to the left it goes, you know that this number is much bigger than this number. This number would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and that's much smaller than 1. Actually, it wouldn't even be that. I'm sorry. Let me undo that real quick. I messed up. It would be 1.1. Okay, so this is a much bigger number. So now you know why on the pH scale, what we said is, or what scientists said is, 1, I'm lazy and I don't want to write all this. And 2, nobody knows what negative numbers are, so we'll erase the negative. And we'll just tell everyone that 14 is smaller than 1. And that'll be clear, right? No, it's not clear. But now you know that that number is actually the exponent, the negative exponent of a power of 10 logarithm. Again, you don't need to know the fancy language, but that's why on the pH scale, it goes from 7 being neutral, 1 being the biggest, and 14 being the smallest, because that 1 actually represents the negative exponent to a base of 10. And that 14 really is the negative exponent of a number to the base 10. Okay, so if you have a 1, that's a very high number compared to 14 of hydrogen ions. And that's the basis of the pH scale. Okay, acids or any chemical that tend to release more protons, that's the basic thing you want to know, is that acids release protons and bases will accept them or remove them by binding up the proton. Okay, buffers do both. Buffers, and we'll talk a little bit about buffers in the lab today and or tomorrow. Thank you for listening, and as always, have a great day.